Okay, guys. How do we do? Aromatic?
Yeah.
6 pi electrons, cyclic conjugated system, yay.
Yay.
Fetal crafts, question? Yeah, assuming it's planar. Fetal crafts isolation, got an orthopara, stronger director here. It's going to go orthopara to the group 1. How does that look? Looks good to me. Bromination, got 3 groups here. Alkyl groups are going to be stronger directors than the chlorine. This directs orthopara. This directs orthopara. They both direct, both alkyl groups direct here. Which one's going to be favored? Right. We prefer here because it's less sterics. Here it's between the 2 groups. How's it look? Question?
Wouldn't it be better to between that because it's reinforced? Like
Wouldn't it be better to do where?
if it's in between the 2 alkyl?
It's also reinforced here. This is paired to the, it's paired to this and ortho to that. They're both reinforced by the alkyl groups. So sterics, you can avoid steric congestion. So if you want to just show one product like I asked you to, that would be it. How do we do? Bad?
Yeah, I put it between the 2 alkyl groups, but now I know why.
Good. We learned from the quiz.
Yes.
Copper chloride. Diazonium, copper chloride.
Does it need acid?
No, it doesn't. You need acid to make the diazonium. But, this is reduction of the ketone, deoxygenation. You can do Clemmensen reduction, which is zinc, mercury with ACl. You can do hydrogen platinum carbon, or you can do hydrazine hydroxide, which is called Wolff-Kishner reduction. 3 different ways. We've not looked at the mechanism for any of those ways. Mechanism. Protonate the alkenes, just like organic 1. Secondary cation. We can do a hydride shift, make tertiary cation. The ring attacks tertiary cation. But we need to attack tertiary carbon, right? Here, sigma complex. You don't have to draw resonance structure to this. That's what it said. If it did ask you to draw resonance structures, I know you would all be able to do that. Something removes the H, restores the aromaticity, gives final product. How we do? Question? Question? Can't hear, guys. More stable position. What do you mean move it to the more stable position?
Put it on the tertiary carbon instead of the secondary.
This cation here?
Yeah, doesn't matter if you move it
Move it where?
into where the H is coming from. Just do like a hydride shift.
Why? Well, you theoretically could. I've never really considered that. You theoretically could. I mean, it matches carbon-cation arrangement. And then you eliminate, you get the same product,
Yeah,
right?
you get the same.
Yeah. There is, I think, some reactions like that. There's something called the NIH shift, which may be something like that. Not bad. Good, reasonable movement. Okay. Pink sheet, we also have multi-step synthesis, which is, I think, was our white sheet that I passed out. Lab this week, pretty much you're doing what you need to get done. This point forward, we're no longer doing something kind of each week. You now have to choose, okay? Hopefully the directions are clear for what you need to be doing. Some of you did not do the diazonium last week. A few of you will be doing the diazonium this week. Some of you have asked about repeating the diazonium. I would not repeat the diazonium. I would do some of the other reactions. If you have any questions, please ask. A couple things about housekeeping, guys. Reagents, you have to put the caps back on them when they're done. Okay? There's toxic reagents like acid chlorides. Look over there, the cap's just sitting off. Nobody's near it. Sodium sulfate, cap's off. Sodium sulfate's anhydrous. Leave the cap off, it will no longer be anhydrous. Okay? You go to the biology lab and you're working with snakes. Do you leave the cage open to the snake? I hope you don't. Okay? Cleanliness. I need you to clean the hoods when you get through with them each day. Okay? Also, by the way, when you put reagents, when you put the caps back on reagents, it's not just setting the cap up there. It's actually twisting the cap. Right? All the time I pick up and the cap is just falling off. Basically a little bit more prudence in doing these things. Now you don't want to tighten the cap so tight that the cap cracks because it's plastic. Sometimes I do that myself. Just tighten it up a little bit, okay? Those that are doing these things, I appreciate it. Those that are not, I'm asking you to pay a little bit more attention to things. There's some other things. I should have brought my list. At the beginning of lab this week, I may mention a few other things we need to kind of focus on. Okay, we're looking at the other two substitution mechanisms, NAS, and Benzyne. These we substitute what looks like more of a traditional leaving group. In EAS, we typically substitute an H, replacing an H. Here we have what looks like a leaving group from our SN2 type reaction. Okay, we were doing this reaction here. We said that we can get spectator ions going, and we can get this to attack here. And this pi bond is going to move this way, break the pi bond, and this gives this. We said this reaction does not work as shown. The reaction doesn't work with mild heat. But I said if you put like a ketone here, ortho to the leaving group, ortho or para, okay, or para. Why ortho or para? Because when we did resonance structures, here's our original anion, which fell ortho to the leaving group. We did resonance of this, and we showed here, which is para to the leaving group. Then we did another resonance structure back to ortho to the leaving group. The minus charge, the lone pair, falls ortho or para to the leaving group. It turns out, if you put a strong electron withdrawing group ortho or para to the leaving group, where the anion falls, the reaction will now work. There's a variety of withdrawing groups. A carbonyl is a classical one. Nitro is also very classical. Why does it now work? Well, now you can draw an extra resonance structure. Now we can go this way, electrons here, and move these out. We'll call this, all the others can be A, we'll call this B. And what does this arrow movement give? Double bond out here. Electrons onto the oxygen, now 3 long pairs. It's It's a minus. I think you can see that. And nothing happening over here. Now, if the group is pair, we could also do that extra resonance structure. Or if it was in the other ortho position. Because I placed it here, boom, additional resonance structure. Not only is it additional, it's also better than the other three. Why is it better than the other three? Minus on carbon or minus on oxygen, which is better? Yes. Putting that minus on an electronegative oxygen really stabilizes the intermediate. And now it will actually work. What we take from that is now the intermediate is stable enough that it can be formed in the rate determining step at a reasonably mild temperature. So this is your major resonance structure. We will state this moving forward again. Anytime you do a nucleophilic addition to a pi system, you typically can only do that if the resulting anion is placed on a heteroatom. And indeed, it is placed on a heteroatom right there. We'll see that again. So, if you put a group there, the reaction will work. So if we look below, this is a nucleophilic aromatic substitution. There were two steps. The first step was what? Addition. The last step was when we eliminate off the leaving group. You can work with any resonance structure. Probably easiest to work right here, and we move these here and kick that off. We call that C. And that gives our final product. I've moved it. It's no longer there. Of course, you can work from this resonance structure. We can move these here, we can move these here, and we can move that off. That would also give that. You can work with any resonance structure anytime. Don't ever let anybody tell you you can't. Okay? It just may require extra arrows. Of course you can. This is just really one structure. It's like one color composed of 4 different primary colors. Okay, what's the requirement to do an NAS?
Electron withdrawing group ortho para.
There you go. A strong electron withdrawing group, ortho or para to the leaving group. Why? Because resonance will then allow you to typically put the anion on a heteroatom by resonance. What's the rate determining step for an NAS? What are the 2 steps? Addition and elimination. Which one's the rate determining step?
Addition.
Addition to form the anion. Question. In which step does the leaving group leave? Aha! Which step does the leaving group leave? Addition or elimination? The elimination, the second step. Is that the rate determining step? No! The leaving group leaves in the fast step. Or we can say the leaving group does not leave in the rate determining step. Now if you go back and look at your SN1, SN2, E1, E2, all 4 of those, the leaving group leaves in the rate determining step. But in this mechanism, it leaves in the fast step, the non-rate determining step. Because of that, your leaving group requirements are not as strict as all your other SN1, SN2, E1, E2. Where typically those you have to have like iodine, bromine, chlorine is okay, or like tosylate, or protonated oxygen. And there's a couple, protonated nitrogen. If the leaving group leaves in the fast step, and we'll see other mechanisms where it does during test 2, 3, and 4, just about anything can leave. If you've ever seen it as a minus, it can probably leave in this fast step. The only thing that typically will not leave is like a plain carbon or a hydrogen. But even then, I'm kind of lying to you. But don't do it in this class. Okay? Leaving group requirements are not as strict when the leaving group leaves an 8-fast step. Actually, in terms of leaving groups, of the halogens, your fluorine is your best leaving group for this mechanism.
What? That's absurd.
Why is fluorine the best leaving group? Let's go back here. Let's consider we have our requirement there. It could be a nitro group. Nitro is very good. If we switch the S to F, the reaction is faster. Why? Why is the reaction faster?
It's stronger stabilized.
There you go. Stronger dipole right here. Because there's a stronger dipole, it gets this guy more interested in that guy. Bam! I'm coming in. I like positives. Ooh, even more positive. And the more separation of charge you have, the more attraction you have. And that leads to an easier reaction, a lower energy reaction. The leaving group leaving, in our traditional sense from organic 1, that's the fast step. So you can't say iodine's a better leaving group when it's not applicable here. So next time you're talking about leaving group abilities, make sure you clarify which mechanism are we talking about. Okay? This weekend, you know, for the big game, you're talking about leaving groups. Which mechanism are we talking about? So fluorine's actually your best leaving group in NAS. That make sense? Okay, let's do some examples here. What do we have here?
Fluorine.
I've got a ring. Oh, rings like to do EAS chemistry. I can brominate it. If I brominated this, where would the bromine go?
Is it a fluorine?
It would go ortho to the fluorine. But the bromination would have to be an electrophile, the electrophilic bromine. What am I reacting this ring with here? Is this an electrophile or nucleophile? That's S minus. Get rid of spectator ions. Group 1, group 2, spectator. Mark them out. That's S minus. Do you do is the ring going to do an EAS and attack S minus by EAS? No. You've got to understand first that you have a nucleophile. Since you have a nucleophile, we're doing either NAS or benzyne. We haven't covered benzyne yet. Which one are we doing here, NAS or benzyne?
NAS.
How do you know? After we cover it, how do you know which one we're doing? NAS is the easier mechanism. And if NAS can occur, do NAS. We'll say that later. Can you do NAS here?
Yes.
Do you have a traditional leaving group? What do you want to be the leaving group?
Fluorine.
Does that fluorine have a strong electron withdrawing group, ortho or para?
Yes.
Yes, the nitro. If you draw it out, you're going to see a pi bond. You can do resonance just like we did with the ketone. This is set up to do NAS. You've got to assess the reaction. And I've already showed you the product. How about that? Does that look right?
Yes.
If we want to balance that, what do we show? NAF. F minus was the leaving group. And your mechanism, we just went over it before. Solvent? Yeah. Usually I'll leave solvents out. Occasionally I'll put them in because you do need to sort of get some exposure to solvents. And when I say exposure, I mean sort of intellectual exposure. Toluene will dissolve this salt. It may not dissolve in toluene. Acetonitrile is a good solvent. THF. Solvents are something we rarely talk about too much, but it's a big topic. Solvent selection. Okay, here's one down here. Wow, tetrasubstituted benzene ring. Ammonia. Is ammonia electrophile or nucleophile? Nucleophile. I mean, would you ever envision some nucleophile attacking ammonia? I mean, it has no dipole leaving group. I mean, is ammonia a base or an acid? Base. Bases tend to be nucleophiles. They have the electrons that they want to go do something. It's a nucleophile. It's a neutral nucleophile. So we're not doing EAS. So we're either doing what? NAS or Benzyne. Can you do NAS here? Yeah.
Because it has a sign on.
Now I've got 3 potential leaving groups, a bromine, a chlorine, and a cyano. Actually up here I had 2 potential leaving groups. Why did the nitro not be the leaving group?
It's the electron withdrawing group.
If this was a leaving group, does it have a strong electron withdrawing group, ortho or para? Fluorine is not a strong electron withdrawing group. Strong electron withdrawing group is group 4 from the EAS discussion. But that one does. Okay? Which group? Yes, bromine. Cyano's a group 4 strong electron withdrawer, but it's matter to the bromine, both of them. But the chlorine has one ortho and pair. Terminology. We would say that the chlorine is activated towards NAS.
So Dr. Stevens, you were saying that the bromine was still an option even though chlorine is higher up on the table and more electronegative. So would that be the determinant or would it be the fact?
No, bromine is not an option.
No, I was saying you were, so the determinant is not just that chlorine's more electronegative, but that it's got the 2 withdrawing groups, ortho and para.
Yeah, first you want to make sure you have the requirement.
Yeah.
This leaving group does not have a strong electron withdrawing group ortho and pair.
Okay, so I just like.
So it's out.
Yeah.
Now, if you had 2, then you might look at, well, which one's a better leaving group?
Okay.
Yeah, I think the question is if you remove that bromine up a carbon, what?
Move it here?
Yeah.
Well, then nothing is activated towards NAS, and you can't do NAS.
But they both are.
What do you mean they both are?
They would both be.
Ortho and cyano.
Oh, yeah, you're right. Okay, the bromine. Oh, then they both would be, and then you
Yeah.
may look at, well, which one's a better leaving group?
Yeah, those are, I think that's the question.
Chlorine's a better leaving group than NAS, but it's more electronegative. In this reaction, the cyano groups are activators. What are they activating? They activate the NAS mechanism. They're making the chlorine susceptible to being substituted. But hold on, I thought a cyano was group 4 deactivator. That's for EAS. Okay? The cyanos activate the chlorine for NAS mechanism. Don't confuse your mechanisms. When we say activation, we got to say, well, which mechanism are we talking about? So, ammonia displaces the chlorine. It's got to lose, after the nucleophile gets there, it's got to lose an H. At the end, you have, before the end, you have this. It has to lose an H to go neutral. The chlorine leaving group can take the H, form HCl. So if you work through that, that's where the H has to go. Up here, see, this is already missing an H. And you make sodium leaving group. Does that look pretty straightforward? These are good old NAS reactions. Here's one here. This is a little more complex, but this is how you make the antibiotic known as ciprofloxacin. One of the last steps is to take this here, react it with this diamine. We're doing NAS, kind of obviously here. What chemistry can we do here? I see two fluorines here.
The bottom fluorine.
Is either one of these activated for NAS by a strong electron withdrawing group, ortho or para?
The bottom
The
one.
bottom fluorine.
Yes. Talking about this F here. See, that's para. That's a ketone. Does this one have a strong electron withdrawing group, ortho or para?
No.
The amino is not. No. This guy is displaced. Now, one thing about this reaction, you do have an acidic proton here.
That was my question. Under what conditions would that be acid-base?
Acid base is always instantaneous and fast. This is basic enough. This will take the H first. And so you probably need two equivalents of this. And the product here is going to be you can show this is minus. Also, this can react on both ends. They probably use a huge excess, so it only reacts on one end. So there are some details here. But this comes from NAS displacement of the activated fluorine. You're probably going to have to work this up with the appropriate acid to put this on. Basically, that's the product that comes out of here. Again, there's details to it. And that right there is cipro. That's ciprofloxacin. And we hopefully understand why this is the fluorine that's displaced and not that one. We can do mechanism, we can draw anion, we can do resonance into the carbonyl and show the anion on that oxygen. How about the last one? What's the product?
No reactor.
Yes, no reaction. Why? This compound does not contain a potential leaving group with a strong electron withdrawing group, ortho or para. By the way, a nitro can be a leaving group. But does the nitro have a strong electron withdrawing group, ortho or para? No. No reaction at mild temperature. It's no NAS reaction. Definitely no NAS. It might be a Benzyne mechanism. But Benzyne requires pretty harsh conditions. Or a stronger nucleophile. So, no NAS.
When we say mild temperatures, what are we talking, like refluxing or?
Of course, it's all kind of a moving scale. Room temperature would be mild. 300 degrees, would you call that mild?
No.
That's going to be more like not mild.
So
know to be like extremely obvious.
Right, it would be like 75.
Yeah.
So yeah. When we see more examples, it'll hopefully be a little more clear. Here's a synthesis of olanzapine, an antipsychotic drug. And right here, going from 22 to 23, they're doing an NAS reaction. This is your nucleophile, and they're displacing the fluorine that has a orthonitro group. And they're making what bond? Right there. So the fluorine is now gone, replaced by the nitrogen. You can practice that mechanism right there. Good old NAS. I don't know if it's here, it may be in the outline. Anybody ever heard of the Sanger reagent? It's used in biochem. Sanger reagent is where, I think there's just one more fluorine here. Or maybe it contains 2 nitros. You have to look it up on the wiki. Sanger reagent, it's a reagent for, I think, functionalizing amino acids, or testing for amino acids. And it's basically an NAS mechanism. But you may see the Sanger reagent in biochem. S-A-N-G-E-R. I think it's got 2 fluorines. But the amine from the amino acid displaces one of the fluorines in the reaction. Okay. Let's look at the Benzyne mechanism. This is a second mechanism for nucleophilic substitution. It can occur when there's no strong electron withdrawing group. It requires harsher conditions than NAS, or a very strong nucleophile. If you take chlorobenzene, react it with KOH at room temperature, there's no reaction. Hydroxide. But if you react it with hydroxide at 300 degrees Celsius, and put a lot of pressure on it, like at 2500 psi, force it to come close together, we can get a reaction. You work it up with acid and you can get phenol. Basically the OH can replace the chlorine.
Is there some danger involved in that reaction?
Danger?
Yes.
Well, I mean, it's usually done in what's called a bomb. It's a like a chamber, like iron, it's like a metal, and you screw it down so it won't open up.
Why do you have to do the acid work?
We'll see, because that's acidic,
Oh,
and this is basic.
okay.
And I'll also give you a wonderful analogy of what happens when you have an acid-base reaction. Okay, mechanism. So, what do you want to do? We got hydroxide. Do you want to attack here and kick off the chlorine? All at the same time?
No.
No, that looked like SN2. Don't do that. Do you want this to ionize off, make cation, and then attack?
We should make a benzene.
No, that looked like SN1. Don't do that. Do you want this to add here and move the pi bond down like this?
That's like, that's NAS.
We should make a triple bond.
You want to do that?
Well,
So that's NAS. And we know that that doesn't occur unless you have another group here, like maybe a nitro. So if it don't occur, then don't do it. So we got to come up with some other mechanism. What else could we? How else could we do this? Well, here we go. It's wild and crazy. But what happens is this H next door, this guy, if you beat on it, okay, this is harsh conditions. Make something happen here. This will take the H. And make an anion plus water. Just an acid-base reaction. But see, that's not that acidic. You really have to drive this, force it to do that. Now, back in Organic 1, we talked about why something would be acidic. Does this have any stability going for it? What stability does it have that you can make an argument? You're a lawyer making an argument here. You got to.
Van der Waals interactions.
Van der Waals interaction. How about something else, Rosbina? Carbon's sp2. And so at least it's got more S character than sp3. And the more S character, the more acidic. Look back at your acid-base handout from week 1 of Organic 1. Okay, we talked about hybridization effect. Okay, it's still tough. But from here, this is then known to move in and kick off this. And what does that give?
Benzyne.
That gives a triple bond in the ring, like an alkyne, Y-N-E ending. That's called a benzyne. That's what a benzyne is. Where does it come from? What do we do here? We eliminated HCl. That's what we did here to get that. I showed it as a two-step process. Now, is this a E2 elimination? Did I do an E2 elimination? So E2 would have been boom, boom, all at once and go straight there. Did I do an E1? No. This we made an anion. Let's try to finish this up in 30 seconds to a minute. Let's see what we can do here. We'll talk more about this. I'll just finish up the mechanism. At this point, the water, this is a very weak here. The water then will add, actually either carbon. They're symmetrical. Okay, you can add to either one. I'll add here, it doesn't matter. You add there and push the electrons there. That gives that, what's here now? We push the electrons in, that. Now you've got a strong base. That's a proton source. That looks like H3O+. You're going to have what? A proton transfer. That will give an H there and an OH here. And what is that? H plus transfer. We'll talk about that next time. That's not actually the end. We're under basic conditions. There's hydroxide around. This is acidic. Hydroxide will take the H and this is in step 1. What's the purpose of the H3O workup, Nick? Put the H on the oxygen. If you make an acidic product under basic conditions, it will be in the basic form. You can't say hydroxide. Once the product's made, I don't want you to deprotonate it. It won't listen to you. It'll go deprotonate the product. There's some details here we'll look at next time. We'll also look at multi-step synthesis on Friday. We'll see if there's any questions about spectroscopy. don't expect too many. It's just like test one. Okay, guys, have a good day.